Okay, we're going to start section 5.2, moving into some of the different rules for probability. I know that in the last section we really used some simulations to try to mimic or imitate this chance behavior, but we're going to move into some different probability formulas. Now, some of these things you are already familiar with. For example, it's very likely that you are already aware that when we talk about probability, it's always some number that is between 0 and 1. Okay, probability is always a number between 0 and 1. And if you were to sum up all the probabilities for all of the possible outcomes, it should always total the number 1. Okay, should always total the number 1. So if all the outcomes in a sample space say that you were going to roll a single dice, or single die, were equally likely, okay, say they were all equally likely, the probability that event A occurs could be found using this formula, okay? And you take the number of outcomes in the numerator and you divide by the total number of outcomes in the denominator. For example, if we wanted to find what's the probability that we would get a sum of 3 when rolling 2 dice. Okay, and you can see pictured at the bottom of this page, actually, this is the entire sample space for rolling 2 dice. Okay, so we're going to say the first one is kind of this orange color, the second one is this light green color, and so this is all of the possible combinations of rolling 2 dice. And if we wanted to know, well, what is the probability that when you roll 2 dice, the sum would be 3, let's look down at our sample space here. It looks like here's one situation where the sum would be 3 if the orange die were 2 and the green was a 1, or if they were reversed the other way. There's another scenario where the sum would be 3. Now, there were 36 possible outcomes in the sample space, but only 2 of them were what we would call a favorable outcome, representing the sum of 3. And so we take the number of favorable outcomes over the total number of outcomes possible. I could reduce that to 1/18th, although they will not take off on the AP test if you do not reduce your fractions, okay? But here's kind of the general formula for finding the probability of an event. Okay, now this is really important here, this last little note here. It says the probability that an event does not occur, okay, so we're talking about the probability of the event not occurring, can always be found by taking 1 minus the probability that the event does occur. And we call this the complement to that event, okay? So if I tell you the probability that it is going to rain is 20%, you could calculate the probability that it's not going to rain by saying 1 minus 20%, and there's an 80% chance then that it would not rain. Okay, so as we mentioned before, we said the sample space is the set of all the possible outcomes. When you hear the phrase probability model, what that's talking about, there are 2 parts to a probability model. Okay, one is if you were to look at the sample space, we'll call that S, okay, you have to first list all of the probabilities for each possible outcome, okay? So you have to have that listed in a probability model, and all the probabilities have to be between 0 and 1, and they have to sum up to be 1, okay? So you're listing all the possible outcomes. Every probability has to be between 0 and 1, but if you were to sum up all the probabilities, they must total 1. So for example, we could say the sample space for tossing a coin, your options are either to get heads or tails. The probability of heads is 0.5. The probability of getting tails is 0.5. We can see those probabilities are both between 0 and 1. They also add up to be 1, okay? All right, and then at the bottom here you see there are 36 possible outcomes there for that. So let's go ahead and flip to the next page here where we look at different ways of kind of representing or calculating probabilities. And we'll look at each of these in more detail. But basically, you could use a Venn diagram. You could use a table or a chart of sorts, or you could use a tree diagram. And again, we'll break tree diagrams down in a little bit more detail later, but I just want to draw your attention to this. Tree diagrams kind of work in columns like this. This particular tree diagram is talking about having a coin, and you're going to toss the coin 3 times in a row. Typically, tree diagrams are most beneficial when you're talking about a sequence of events. One thing happening, then something else happening, then something else happening. And so those events in sequence are designated in these columns, and you can see for the first toss, the options are heads or tails. And then from that, this is why we call this a tree diagram, because we get these branches. The second toss could have been heads or tails if the first one were heads, or the second toss could be heads or tails if the first one was tails. What I want to draw your attention to is the fact that in the end, this sample space column that you get here, we're getting that from moving across the branches. So for example, if I were to move across the branches in this fashion, heads on first, second, and third toss, that's how I'm getting HHH there. Okay. Now, if I were to move a different path, let's say heads on the first and second toss, but then tails on the third toss, that's how I'm getting heads, heads, tails. Okay. And so you can see if you were to flow across the branches, each possible sequence, you can see that we have 8 possible outcomes here. Each one has a probability of 1/8 occurring. So if I were to fill in a 1/8 underneath each one, these would all still add up to 8/8 or 1. Okay. All right, so let's just look at this one example here at the bottom. Of course, when we're talking about an event, a lot of times we designate an event with a capital letter and then we define what that letter is. Here we're going to define event A as rolling a sum of 5 with 2 dice, okay? And on the previous page here of your notes, I had listed all the sample space of rolling 2 dice. You could see all the 36 possible outcomes, but of those 36, there really are only 4 that are favorable, 4 that show a sum of 5. Okay, so if I were to set up, well, what is the probability of event A? I could say, well, 4 of the 36 possible outcomes would result in rolling a sum of 5. Okay, I could reduce that to 1/9, but I certainly do not have to do that. Okay. All right, so let's take a look and see if we can determine whether what we're given here in this table is actually representing a legitimate probability model or not. Okay, so here we have the scores you can get on an AP test, 1 through 5, and this represents the allocation of the 2014 AP Statistics exam. So this is saying that there were 22.3% of the students got a 1, or in other words, the likelihood of getting a 1 is 22.3%, 18.3% for a 2, and so on. So the question is this actually a legitimate probability model? Well, there's 2 things you have to check. 1, are each of these probabilities numbers between 0 and 1, and we can scan that and say, yeah, that's true. And then the second thing we need to check is we need to make sure that all of these probabilities are adding up to a sum of exactly 1. Okay, and I believe if we were to do that, we would be just a little bit shy of 1. Okay, so I'm going to say that no, this is not a legitimate probability model, and my reason is because the probabilities do not sum, okay, because the probabilities do not sum to 1. Okay. Now, if I were to make this a legitimate probability model, you know, I might come in here. It's telling me here in part B to go ahead and change that to 0.126. I believe that makes this now sum to 1. And then it says, find the probability that the chosen student either scored a 3 or better, okay? So the way we typically write probabilities is we put a little p, and then in the parentheses we define what the event is, okay? So I'm going to just put 3 or better. Okay, so that means I would want to take the probability of getting a 3, a 4, or a 5, and I would want to add those up, and I would roughly say that you've got a 58.5% chance of essentially passing the AP test if you took it in the year 2014. Okay. All right, let's try another one here. In example 3, again, same question. First of all, is this a legitimate probability model? I'm glancing at these probabilities. I see that it meets the first criteria, that all the probabilities are numbers between 0 and 1. However, if I were to add these up, I think, again, we're just a little bit shy of these summing to 1. So I'm going to have a similar answer to what I had on the previous problem. I'm going to say no, because the probabilities, okay, because the probabilities do not sum to 1. Okay, has to sum to 1. And so then it says here in part B, add F to the sample space and fill in the probability. Okay, so I'm going to add F, and so if this is the entire sample space, A, B, C, D, and F, then I have to take whatever lingering probability would need to go here so that this would sum up to 1. Okay, so I believe that that would be 2% chance of getting an F. Okay, then it says, now find the probability, and read this carefully here, that the chosen student did not score a B. Okay, so we're looking for the probability that they did not get a B. Okay, communication is always key in AP Stats. You want to make sure, you'll notice I'm labeling this. I'm not just writing a kind of a naked answer down. You always want to label what that fraction that you're going to, or decimal that you're going to be putting down represents. Okay, now remember what we said earlier. If you find the probability of an event not occurring, that is the complement to the event occurring. Okay, the probability of an event plus the probability of the complement to an event, those always add up to be 1. So I could say the probability that they did not get a B would be the same thing as 1 minus the probability of getting a B. Okay, so that would be 1 minus 0.40 or 0.60. Now, this was a very small probability model. There were only 5 options in the sample space. So could you also have answered this question by simply adding up the probabilities for A, C, D, and F and get 0.60? Absolutely. Okay, but you definitely want to keep this in mind. It is very, very helpful for many problems here. Okay, so let's look at example 4. It says, online learning courses are rapidly gaining popularity among college students. Randomly select an undergraduate student who is taking online learning courses for credit and record the student's age. Here is the probability model. Okay, so we have these ages, and this is the likelihood that people that fall in those age brackets would be taking an online course. Okay, so again, we start with the question, is this even a legitimate probability model? I see these are all between 0 and 1. If I were to add these up, they do all sum to 1, so I'm going to say yes. Each probability is between 0 and 1, and all probabilities sum to 1. Okay, part B says, find the probability that a student chosen at random, okay, that the chosen student is, look at this keyword here, not in the traditional college age group of 18 to 23. So I'm looking for the probability that they are not between 18 and 23 years of age. So I could do 1 minus that they are between 18 and 23, and that would land me at 0.43. Okay, 0.43 here. Okay, let's go ahead and flip to the next page here. Talk a little bit more about complements here. When there is a special symbol for a complement, we've said that the complement is referring to that an event did not occur. But if we were to define event A as being that an airplane takes off on time, the symbol that we use to represent a complement to an event is to put a little c in the exponent, okay? A to the c means that the airplane did not take off on time. Okay, so in other words, the complement of A, we could calculate it like this. The probability of A not happening is equal to 1 minus the probability that A did happen. Now, if you look over here in this box, we're going to say that everything inside this circle represents event A occurring, and everything outside the circle represents the complement to A, or in other words, that A did not occur. Okay. The whole sample space, though, is everything included inside the entire box, including event A. So these two events would add up to be a 1. All right, so let's look at example 5. We are going to let X be the number of car repairs in a given year. So either 0, 1, 2, or 3 or more car repairs in a given year. And then the bottom row represents the likelihood or probability of having that many car repairs. Okay, we're going to let B, event B, be a car requires less than 2 repairs in a year. Okay, so that means, keep in mind here, X is the number of cars. Okay, so if we're looking for the probability of event B occurring, I'm just going to spell that out. That is that the number of car repairs is under 2. Okay, so I'm not actually counting the 2. It said less than 2. Okay, so that means I'm really only counting these 2 options right there, that you had no car repairs or just 1 car repair. Okay, and that would be simply adding those 2 probabilities up and saying that essentially you have a 75% chance of having less than 2 car repairs. Now let's look closely at this. Now we want to find what's the probability, and this is B with a little c there. So that means that you have a car that is not requiring less than 2 repairs. Or another way that you could say this is the probability that the number of repairs is greater than or equal to 2. Okay, whoops, didn't mean to do that. Let me cut this here. Okay. Okay, so the complement to the number of repairs being less than 2 is that the number of repairs are greater than or equal to 2. And so then we would go through and we would add up those probabilities, getting 25% for that likelihood. Okay, now it's asking us to interpret what this answer is representing here. Okay, so we could say this a couple different ways. We could say a car requires 2 or more repairs in a year is 25% likely. Okay. Could say 2 or more. That probably makes more sense to word it like this than to say not less than 2 repairs. Okay. Okay, so anytime we're talking about events occurring and probability, we always have this idea of what's called 2 events that are mutually exclusive. And so when we talk about events being mutually exclusive, we're talking about 2 events that it is completely impossible for those 2 events to happen at the exact same time, okay? So, for example, you could not have a student who is both a junior and a senior at the same time, okay? So you can see this demonstrated here in this Venn diagram. Again, everything in the rectangle represents the entire sample space, but you'll notice how the 2 circles designating event A and event B, they have nothing in common at all. So they are completely separate. So what we're asked to do here for this problem is we're asked to read the 2 events, A and B, and decide whether we think that they are mutually exclusive, which means they could not occur at the same time. Okay? Or if they're not mutually exclusive, which means they could occur at the same time. So the event that you're performing is you're going to roll a die 1 time and you're going to record its face value. Event A is that you rolled a 6. Event B is that it was an even number. And so you're asking yourself, could these 2 things happen at the same time? Absolutely. A 6 is an even number. So we are going to say that this is not mutually exclusive. Okay, this is not mutually exclusive. Okay, let's look at example B. The event is that you flip a coin and you roll a die, you record the coin toss, and you record the number shown. Okay, event A is the coin was heads, And event B is that the die shows a 6. So again, the question you're asking yourself is, could you do these two things, flip a coin and roll a die, and both of these things, events A and B, happen at the same time? Okay, and absolutely, you could do that, and the coin could land heads, and the die could land on 6. So again, we're just going to say these are not mutually exclusive. Okay, let's look at C. Here again, we are flipping a coin and rolling a die, recording those outcomes. Event A is that the die showed a 4. Event B is that the die showed a 6. And so this is really disregarding altogether anything that you did with the coin. You only rolled a single die. It is impossible for, in one roll, for it to be both a 4 and a 6. And so these events, A and B, as they're defined here, those would be mutually exclusive. Okay, those would definitely be mutually exclusive. And then the bottom one, letter D, the random phenomenon is that you are observing the weather on a given day. A is that it is raining, and B is that the sun is shining. So is it possible for it to be raining and the sun be out at the same time? You often don't see that very much, but it definitely is possible. So we're going to say that these are not mutually exclusive, okay? Not mutually exclusive. That will be a term that will be very important that you understand what the phrase mutually exclusive is referring to. Okay, we're going to wrap up with this page here. I want to make sure that you are familiar with some of this notation. This symbol that looks like a U is the symbol for or, okay? We'll call that union. And then when that's flipped the other direction, that's actually the symbol for and, okay? And I try to remember this because when I see the symbol flipped for and, I almost think of it as being like a lowercase n, and has that lowercase n in it, okay? Now, it's important that you understand the difference between or and as it relates to probability here, okay? Sometimes the or can be a little confusing because we think that it has to be one thing or the other, which is true, or it could be both. Like when you go to a restaurant and the waitress asks you, would you like cream or sugar in your coffee? She's really saying, do you want cream? Do you want sugar? Or would you like both, cream and sugar? Okay, so when we say or, we're talking about it could be anything in event B, or A, anything event B, or it could be anything in both events A and B, like where they're overlapping. As opposed to an intersection for and, this is only talking about where they overlap. So if event A is the probability of someone liking salad, and event B is the probability that someone likes meat, the probability of A intersection B is only where those two events overlap, that someone would like both salad and meat, okay? All right, so there is a formula. It's actually on the formula sheet for how to find the or probability, okay? But it doesn't use the word or. This right here is how the formula looks on the formula sheet. It uses that notation for union, okay, for union there, okay? So we've already talked about the formula for the complement of an event. We will learn later a little bit about how to do the intersection, but I want to focus here on this probability for or. You calculate the probability of event A plus the probability of event B, but look at the end of the formula. You're subtracting off the probability of A and B. And if you were to look at just this Venn diagram, the probability of event A would be all of that. The probability of event B would be all of this. And so if you look closely, you notice we counted this intersection part here twice. That's why at the end of the formula, they're saying to subtract the intersection so that that's not actually included 2 times there, okay? Okay, something else that is super important is how to find the probability that none of something would occur, okay? None is always the opposite or the complement, okay, of at least one, okay? So I'm going to have you add this formula here, okay? The probability that at least one, whatever it is we're talking about, occurs is 1 minus the probability of none. Oh, I think I meant to kind of put this right up here where these formulas are, okay? This is something you're going to need to look back at, and you're going to want to commit this idea to memory. And so let's look at one small example here, and then we'll dive more into this formula here in the next video, okay? So if a problem asks you, what is the probability of someone reading at least one paper, in order to calculate that, you would take 1 minus the probability that someone reads no paper or none of the papers, okay? That will give you the probability of at least one. If you think about what at least one means, at least one means greater than or equal to 1, okay? So if you think of it like that at least one means greater than or equal to 1, then if you were to do 1 minus, how could you say the probability of not being greater than or equal to 1? You would say the probability of, another way of saying x equals 0 is to say none, okay? Because you're including 1 and everything greater than 1, so the only thing you could exclude that you would want to subtract from 1 is the probability of none. Okay. All right, let's see if we can just do this quick matching here at the bottom, and this will be a great place for us to stop here in this video. I want to know which of these Venn diagrams represents the complement of an event. Okay, the complement of an event, that would be pictured here in number 3, just this green part that's shaded all the way on the outside, which represents 2 events that are mutually exclusive. Remember, that means that 2 events cannot occur at the same time. That would be pictured in number 4, how there's no overlapping here, which represents the intersection of 2 events. Okay, the intersection of 2 events, that's only this green part right here, so that would be pictured in number 2. And then finally, the union, remember that means or, which means one, the other, or both. And so all of those options are shaded in there. Okay, that brings